All right, good evening, everyone. I'm doing this lecture on Friday night at 8 o'clock, so I have no life. I hope everybody's doing well and everyone's families are safe in this tough time. We hear that we're flattening the curve, so that's good. But what happened with SARS, not to be a downer, but the curve flattened and then it went back up again. But we are taking very good precautions overall with our gloves and our safety masks. So another thing, kudos and great job to everybody. Kudos isn't the right word, but great job to everybody that is in the healthcare profession right now, either helping out as nurses, helping out the doctors, and doing all those different things in the hospitals. You're really needed right now, and you're doing a great job. So again, this class comes second to that. If you're busy with work and have really long hours, don't really worry about studying too much. Let me know that. If you're going to hand in your assignment late, you have to let me know. That's the only thing that I require, is that you could just let me know, and it'll be okay, especially if you're in those essential jobs. Anyway, so today we're going to be doing Chapter 9. So Chapter 9 is technically going to be covered next week, so a week of the, what is Monday? Next Monday is going to be the 20th, so the week of the 20th, because this week is technically spring break. Also, I hope everyone is having a safe and good spring break. You can't really go out and party, but you stay in and party and watch Netflix. So next week we'll technically be going through Chapter 9, and the Chapter 8 homework will be due next week. So for my Tuesday class, it'll be due on Tuesday night, the 21st, and for my Friday class, it will be due the 24th, Friday night. Then after that, Chapter 9 homework will be due the following week on the 28th for my Tuesday class, and May 1st for my Friday class. Then after that, we'll be covering Chapter 11 the following week, and then we'll go into the third exam, and then we'll do a review / Chapter 14, 15, 16 kind of medley thing. I'll post that as well on YouTube, and then we will study for the final and do a big review. So anyway, let's go into Chapter 9. All right, so Chapter 9, we're going to be learning all about different types of solutions. Now, you don't have a chance to experience it in the lab because we can't go into lab, but solutions are basically, we're going to be talking about different types of solutions, but everything is going to be in water. So the solution has two components usually. It's usually everything's in water because we are water-based organisms. All biological life on Earth, what do we need? We need water, right? So that means all of our nutrients, our fluids, our ions, our enzymes, our proteins, our cells, they're going to be in what we call an aqueous solution. So aqueous, I'll write this word down. Where can I write it? Oh, I need to activate my pen. There we go. So aqueous. So aqueous means in water. Very good term to know. So whenever someone says that, and that's why if you ever see in the chemical equations, like sometimes you see NaCl, AQ plus, I don't know, KNO3, AQ, something like that, yields whatever, right? This AQ means aqueous. It means that there is a certain amount of NaCl that is dissolved in water. And we'll learn about how solutions dissolve and all of that stuff today, but basically the solution that we're going to be talking about today all in water. And there's two components. There is, I said this already. Also, it's homogeneous. So homogeneous meaning it's the same throughout, right? You put salt into water or sugar, it's going to dissolve. And it dissolves, and you don't see it anymore. But there's a point at which the salt or sugar or really any substance that you're going to put into the water doesn't dissolve anymore. And that's called the solubility. I call it the threshold, but it's really called the solubility trait. It's really just called solubility. If someone asks, what is the solubility? There's a way of measuring solubility. But I'm going to call it the solubility threshold because that's really what it is, and we'll talk about that soon. Also, okay, so the two parts of the solution. You have the solute, right? So solute is first. Solute it could be any form and is what basically goes into the solution. There's different ways of explaining it, but the salt in, I can't write. How do I undo this? Here. The salt in salt water. So what we mean by that is it's whatever is going into the main component of the solution. in biological organisms and in everything that we study in chemistry, in some things that are relating to our body and health, especially for most of you, there's going to be in water aqueous solution. So the salt or whatever the solute is going to be dissolved in the water. So that's the solute as an example. In this case, this is all water, and the solute is copper sulfate, copper 2 sulfate, if you know your naming. There it is right there. So that's an example of the solute. And solute is copper sulfate is pretty interesting. It's a good one to remember off the top of your head. It is blue. It's this nice, cool blue color when you put it into water. Okay, different types of solutes. Really, it could be anything. You could take a look at this list later, but we just need to know the importance of the difference of the solute and solvent. Then solvent. So the solvent is what it is being dissolved into. So I'll write that down. Solvent is, so what solute is dissolved into. That's what that is. That's what the solvent is. And there are many solvents, but like I said, the one we're going to use here mostly is water. It is what we call universal solvent. It's used in our body. It's used everywhere. There are other solvents. There are organic solvents that are nonpolar. Right? We talked about polarity. Water is very polar, and it is a very good solvent to dissolve a lot of our biological organisms, biological features such as proteins. Our cell, well, it doesn't dissolve cells, but the cells don't like form pellets. They don't form solid material. They kind of swim freely through the water. And the reason why is because of the polarity. So that's important. And if you want to get into more detail, the hydrogen bonds of water is what makes it polar, right? So you have very polar. We learned about electronegativity. So oxygen has a much higher electronegativity than hydrogen does. Therefore, the electrons in water will be pulled more towards the oxygen. If that's the case, there will be an unequal distribution of charges between the oxygen and the hydrogen, making the oxygen negatively charged, or what we call a partial negative charge, right? This partial negative charge from one oxygen will actually interact with the partial positive charge from a neighboring hydrogen atom on a different water molecule. That's the key difference. So there's actually two types of forces. Now, this is more broad spectrum, but it's still important. So there are two types of forces. One of them is called intermolecular. So intermolecular, what that means is between molecules. So this is an example of an intermolecular force, meaning the force is not between, for bond. You can think about it, bond and force are the same thing. So bond equals force. So an intermolecular force, that means it's between neighboring molecules. And usually they're a lot weaker than the second type of force. So now with solutions, we're more focused on the intermolecular forces because we're talking about things dissolving and things not being dissolved, and all of that has to do with the attraction or the behavior molecularly of the molecules with each other, not necessarily with the atoms in themselves, which gets us to our second force, which is called, very similar name, intra. So you see the difference, inter and intra. Molecular, which means between atoms in molecule. I don't know if you can see that, whatever. So we can draw that over. All right. So an intramolecular force is right here. The covalent bond between hydrogen and oxygen is a covalent bond, which is a type of intramolecular force. And the other type, which we learned, and we should know how to name all of these, we have our covalents and our ionics. So this right here, this snippet, is basically every type of bond in the universe. They're either intermolecular or intramolecular. Intra, meaning in between the atoms in one molecule, and those are usually very strong. It's much harder to break a covalent bond or even an ionic bond than it is to break a a bond between the molecules, or an intermolecular bond, like a hydrogen bond, a London dispersion force. There's a bunch of different types, and also a dipole moment, a dipole force, this is a type of dipole force. But I digress. Okay, so water is a universal solvent. Moving on. There are different solvents, yada yada. There's a bunch of them. Yep. So, where can we go? All right. So we'll talk about this next. Basically, since there are different types of solvents, right? There are polar ones and non-polar ones. The ones we like are polar. And one of my students said this a couple years ago: polar bears like water. If you remember that, you're good, because polar means water, and if you have a polar solute, that means it requires a polar solvent to form a solution. So what we're getting at, if you remember from high school chemistry, those of you who took it, likes dissolve likes. Likes, that's one of the key concepts of this chapter. Likes dissolve likes. What that means is, if you have a polar solute, meaning the electronegativity is different between the atoms, and you have a polar solvent, such as water, they are going to easily dissolve in one another. So it's a very, well, it depends on how easy, but they're going to dissolve in one another fairly regularly. So likes dissolve likes. Polars dissolve polar. Polar solute is dissolved by polar solvent. Then the opposite is also true with nonpolar. Oh, there we go. So with nonpolar. So nonpolar solutes require a nonpolar solvent. And there's different examples of nonpolar solvents. Some common ones are hexane. A lot of this you'll see in orgo, if anyone needs to take orgo. Hexane, benzene, benzaldehyde. Maybe you've heard of that one. Butane. So those are some examples. I can go on. Another one common in orgo, cyclohexanone. Yeah, there's a bunch that are non, meaning there's not really much of an electronegativity difference between the atoms. And that requires nonpolar solutes, which can be any nonpolar molecule. You have methane, which is CH4. You could have CO2, things like that. Okay, moving on. So identify the solute in each of the following. So you can pause it right here and do it on your own, but we'll go through it pretty quickly. So 2 grams of sugar and 100 milliliters of water. So you can imagine the sugar is going to go into the water. Therefore, the sugar is a solute and the water is a solvent. 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. Now, this kind of goes into common sense, because you look at ethyl alcohol, methyl alcohol, what's the difference? To someone who's not really experienced in chemistry, there's basically no difference. But you have to go by the amount. So the amount of ethyl alcohol is more, so you can say that you're putting a smaller amount of methyl alcohol into ethyl alcohol. And actually, the structures are not very different. So ethyl alcohol looks like this. It's got 2 carbons and then an OH. That's ethyl alcohol. And methyl alcohol looks like this. It's basically otherwise known as methanol. Ethyl alcohol, otherwise known as ethanol, that is what's in all of our vodkas, or every alcoholic beverage. The alcohol that's in it is ethanol, or ethyl alcohol. Methanol will kill you. It can cause blindness, and it's very toxic to our body. So they're off by 1 carbon. One of them gets us drunk, and we have a good time. I mean, technically, getting drunk is poisoning us, but it makes us. Let's ignore that, because we have a good time. So that's what everyone does. Oh, it's okay. It's just alcohol, right? But methyl alcohol is actually, it's 1 carbon less, and it can kill us, and it's toxic. So it's really bad. Anyway, moving on. So 55 milliliters of water, 1.5 grams of NaCl, and the water is a solvent, NaCl solute. If you ever see water, it's probably going to be the solvent. That's just a rule of thumb. So you can also have solutions of different gases. So solutions don't only have to be in liquid. That's just the way we like to represent them, because they're very easy to visualize and to actually do the experiments. You can see salt dissolving in water fairly easily, and you can do that at home. But gases, you really can't see the dissolution of gases. But gases could go into each other. So 200 milliliters of oxygen gas, 800 milliliters of nitrogen. So you're getting the smaller amount going into the bigger amount. So bigger should be larger amount. I'm too lazy. Bigger amount equals solvent. That's usually the case. That's true. So if you're unsure and there's no water in the equation, whatever one has a larger volume or mass is usually the solvent. Okay, nice, good job. Okay, which of the following solutes will dissolve in water? All right, so this is a good question for the test. Now, basically, we got to keep this in mind. Things that will dissolve in water. We should write this down. Not figs. Things that dissolve in H2O. All right, 1. Most ionic compounds. All right. So there's something that maybe if you took an AP chemistry or something in high school called the solubility rules. Now, I'm a very nice person, and I'm not going to have you memorize these solubility rules. Now, they're pretty detailed. And basically, there are most ionic compounds, such as NaSO4 is one of them, that is soluble in water. Some of them are not, or some of them are very weakly soluble in water. But a large majority of them are soluble. And one of those rules is all ionic compounds in group 1A or 2A, in 1A, let's just say 1A, doesn't be complicated. So every ionic compound that has a metal in 1A, such as sodium, potassium, those are always soluble. So anything with Na, let's say NaSO4, soluble. So that's good. So we have most ionic compounds. Then we have acids and bases. So acids and bases we really didn't cover, and we're going to cover that in Chapter 11. But just know that they dissolve in water because there's a dissociation between hydrogen and this is an acid, hydrochloric acid. There's a dissociation between hydrogen and chlorine. And when they actually form a solution, you get H+ ions, more concentrated, which makes the pH go down, or that makes the solution more acidic. And then you have Cl-, which they're just going to be floating around as anions. Okay, and then thirdly, you have polar compounds. So you can have most ionic compounds, acids and bases, and polar covalent compounds, right? Because you can't have just to be more specific, polar covalent. So these are the classes that can be dissolved in water. Okay, so which of the following will dissolve in water? We talked about this one already, so yes. Gasoline, it's nonpolar, right? So we know that likes dissolve likes. Nonpolar only dissolves nonpolar. Water happens to be polar. It doesn't dissolve gasoline. I2 is nonpolar. Why? Because if you have two iodines that are bonded together covalently, right, because they're both nonmetal, the pull of electrons, or the electronegativity, is equal for both of the iodines. Therefore, there'll be no net pull, and the electrons will stay right in the middle. Therefore, no difference. So they'll be nonpolar, and they will dissolve in gasoline, but not water. And HCl is a very strong acid. It will dissociate very regularly, and it is soluble in water. All right, so we got those two. Boom, boom. There's our answers. All right, let's move on. So I just posted a Crash Chem video. If anybody follows that, please follow it. I have 106 followers, I think. I want to get it to the department, but the department chair never got back to me. Maybe they're all sleeping because it's spring break. At Crash Chem. Yeah, just follow that. Or you can even, if you don't want to follow it because you feel weird that like you're following an account that I run, you could just look up hashtag Crash Chem, or even, I want to write a hashtag on her. Hashtag Crash Chem BMCC. Either one of those hashtags, if you look it up in the search bar of Instagram, will get you to Crash Chem, and you can look at all the videos. And I posted one a couple days ago about the different types of electrolytes. So electrolytes are pretty simple. Electrolytes, you think Gatorade, right? What does Gatorade have? It has all these nutrients and vitamins and all this stuff that it says it has. Really, it's a lot of sugar. That's why you get energy. But what they mean by electrolytes are simply just ions, charged particles, electro. You think charges, you think electrons, right? So electrolyte, a particle that can transmit electricity through it. In order to transfer electricity, you need to have charge. You need to be able to move electrons regularly. And this is what electrolytes do very well. So there are three types of electrolytes. There are strong electrolytes, weak electrolytes, and non-electrolytes. Well, a non-electrolyte is not an electrolyte, but there's three classes of compounds that we can put into our types or electrolytes. You get what I'm saying. A strong electrolyte. This means that it's an ionic compound or some compound that 100% dissociates in water. So what I mean by dissociate is it dissolves, and not only dissolves, it creates charged particles. So my crash chem actually does a better job of explaining this than I am right now because I have to explain it longer. So if you want to get a good explanation, go there. But in essence, what happens for a dissociation is this. Let's say you put NaCl, salt, into water. You're going to get Na plus Cl minus. When you put a soluble ionic or acid into water, it will dissociate into its charged particles or ions. These are called, this is what makes it an electrolyte. And you can tell by if you put electrodes in the water that now has electrolytes. You put the negatively charged electrode, the positively charged sodium will go towards the negatively charged electrode. Therefore, electricity is transferred there's an electrical gradient in this water now because the ions are there. Plus is over here, minus is over here. So the dissociation of the ionic bonds is what makes electrolytes, basically. So strong electrolytes, to characterize them, we can say most, or we can hear, how about this? We'll say soluble ionic compounds. What that means is ionic compounds that do dissolve in water. If they don't dissolve in water, there's very few that don't, like silver chloride, for example. That does not dissolve in water. So what that means, if you put silver chloride in water, it won't be broken down at the molecular level into pluses and minuses. It will just sit there as a solid, and no electricity will be able to be put through the medium unless you have other ions in there. But basically, it won't be able to conduct electricity. So that's why I say soluble ionic compounds, because there are insoluble ones. Also, strong acids and strong bases. I think I'm not sure, chapter 10 or 11 is acids and bases. Now, if it's 10, that makes sense because this ties into it. So you're going to learn more about that next week during chapter 10, about what makes an acid strong and weak. Okay, so we get the point there. Weak electrolytes. So you can imagine strong electrolytes. All right, so wait, one more explanation. Now, for strong electrolytes, it means every single particle dissociates into its ionic products. You put in 10 billion NaCl's into water, saying it doesn't reach the limit of solubility, you get 10 billion Na pluses, 10 billion Cl minuses. That means it's strong. It's a strong electrolyte. Every molecule dissociates. Dissociation of 100% in water, as long as it doesn't go above the solubility limit of the solution, which we'll talk about that later. Weak electrolytes. So a weak electrolyte only dissociates slightly in water. And what I mean by slightly is usually less than 5%, and even sometimes less than 1%. So it very rarely dissociates. Now, that's only a very few classes of compounds, and they include weak acids, right? You get strong acid, strong electrolyte, weak acid, weak electrolyte, not too hard, and weak bases. And the reason why, again, we'll talk about more next week, but what happens is for this weak acid, HF, hydrofluoric acid, you put it into water, the hydrogen doesn't want to, or the hydrogen, how do I explain this? The electronegativity difference between hydrogen and fluorine is so great, right? Fluorine's the highest electronegativity. Hydrogen is very low. The difference is so great that that makes a stronger bond, right? So and they're very close together, very close. H and Cl, which is a strong acid, is like that, and Cl is less electronegative. So you're going to get pretty distance apart, and this bond is going to be weaker. So this bond is easier to break. Water actually breaks the bond, and we'll talk about how that happens soon, I think, in this chapter. So water breaks the bond into its Cl minus and H plus. Now for something like HF, they have a very strong electronegativity, so the bond strength, or the difference in charges, the minus and the plus, that's bringing them together is very strong. Also, you have a very close bond distance. I'm not sure what it is off the top of my head, but let's just say it's like 2 angstroms. Angstrom is the very small unit that tells us the bond length. So between these two factors, you have a molecule, HF, that does not want to be pulled apart. It's very resistant to dissociation. And these are the reasons why. So that means if you put it into water, water will kind of try to go in between the particles, try to break them apart, but it's not going to have too much of an effect. But it will have some effect. Some of the HF molecules will break apart, and most of them will not. So you'll have a very weak electrical current. So it's still considered an electrolyte, but very weak. So HF is not a good conductor of electricity. So if you put it in the water, it'll get a very, very weak, see, it's very dim light here in comparison to our bright light from strong electrolyte. Okay. Moving on. Hope that makes sense. I feel like I'm doing a bad job of explaining, but I hope you get it. Okay. Non-electrolytes. So you can imagine there's strong, a lot of conduction, a lot of dissociation, a lot of positives and minuses. Weak, very little positives, very little minuses. Most of them are still associated with each other and not really broken down. Non-electrolyte. They do dissolve in water. It's a common misconception. They dissolve, but they do not produce ions in water. This is the key for electrolyte. They have to produce ions in water, not only dissolve. Sugar, proteins sometimes, carbohydrates, fats, sometimes they dissolve in water. You could totally have a polar fat. But they don't conduct electricity because they do not produce ions in water. Here's an example. Here's sucrose, which is just a sugar. Put it into water, it just becomes aqueous sucrose, a solution of sucrose. But there's no positives or minuses that can break off. So here's a question that I'm sure some of you are thinking of right now, at least those of you who are paying attention and not on their phone. I bet I just caught someone on their phone. How do you do that? Anyway, the question is, how do you figure out, by looking at it, which one's a non-electrolyte? Because we didn't really cover types of sugars, types of starches, things like that. We didn't do that at all. The idea is, if it looks really complicated, a big structure, the chances are it's a non-electrolyte. You notice here, this is sucrose. Glucose is very similar. C12H22O11, right? From all of the things we learned about ionic and covalent bonds, you don't really see a place where, oh, this can just break off here and this can break off here, like you do with HCl. HCl, it's very distinct. You can see, oh, Cl can break off into its, I know it's minus anion, and H is positive, usually. It's a +1, is 1 valence electron, right? So that usually, that's sensible. Here, what the hell are you going to do? O11 breaks off into its minus, no. That doesn't make any sense. We didn't learn that. So if you've been following along with the class, you can kind of, oh, how do I do this eraser? There we go. So if you've been following along, you can kind of use intuition. And I hate saying, oh, use intuition to do the homework. No. You can kind of see by the structure which ones are electrolytes. And then the ones that basically don't make sense because they're either too bulky of a structure or you don't really see an ion or some kind of dissociation point, those are definitely non-electrolytes. All right, moving on. Here is a very good table. So you can pause this and take a note on it of different types of non-electrolytes. Something like methanol, ethanol, those are non-electrolytes because this is an organic compound. It dissolves in water, but it doesn't really break apart. The OH wouldn't come off to NaCH3+. That's very unstable. That wouldn't happen. Okay, moving on. So complete each for strong electrolytes in water. All right. So, this reminds me. Lab. So you guys had a lab, and there was some like complete the reaction things. Feel free to call me or set up a meeting, and we can talk about it if you have any questions on it. It's basically just it tells you the type of reaction. So let's say this is going to be a decomposition reaction. So CaCl2, complete each for strong electrolytes. Here's what would happen in a decomposition. Ca2 plus aqueous plus 2 Cl minus aqueous. It wouldn't be Cl2, it would be 2 Cl minus. And the reason why is because when these ions dissociate, it wouldn't be Cl2 dissociating. It would be 2 chlorines dissociating from the calcium. But again, that's about lab. We're focusing this on here and this in here. Feel free to contact me. I'll respond pretty quickly. I've been trying to. Some of you, the emails have been spotty, but I've been trying. Okay. So getting back to this. The reason why it won't be Ca2 plus and 2 Cl minus, or Cl2 minus, is because of this. If you look at the structure molecularly, here's what's happening. You have Ca2 plus, and you have 2 Cls that are -1 each, right? They're not bonded to each other, then bonded to calcium. They're just individually bonded to calcium. To create a good ionic bond, you need the negatives to cancel the positives, just like we have here. When this dissociates, that means this breaks and this breaks. If those break, what do you have free? Ca2 plus, calcium number 1, calcium number 2. You don't have Cl2 as an individual molecule. You have 2 Cl. So I hope that makes sense. If not, you can rewind it. Okay, so then we have this. That's our answer. K3PO4. So you can stop and do it on your own. So basically what's going to happen is you have potassium is going to be positively charged and aqueous. And you're going to have phosphate, PO4, that's -3 charge and aqueous. And potassiums, there needs to be 3 of them. So very similar to this explanation. We can do it over here. So you have PO4, K, I don't know. I'm getting better at this thing. It just takes time. K. Okay. So this is what you're going to have for the ionic compound. Then, when you dissociate, you're going to have PO4. Damn it. I hate being a lefty. I keep pressing the buttons. PO4 -3. And you're not going to have K3. K3 is not a molecule. You're going to have K plus 1, K plus 2. Or sorry, K plus 1, K plus 1, and K plus 1. This is your dissociation. That's what you're going to have at the end. So your answer is going to be this one. And another question. Why isn't PO4 plus, or why isn't it this one, basically? Or like 4 there and 3 there. Why isn't it that? The answer is because PO4 is a very stable ion as a polyatomic ion. So we know that as one of our polyatomic ions. And when you need to know it on a test, I will give you the information. Or you can be a cheater and look it up online. But I will give you the information. So, there we go. All right, moving on. Good job. All right. So which of the following reactions represents the dissociation of a strong electrolyte? All right. So basically, what are we looking for in a strong electrolyte? We are looking for a complete dissociation of the ions. We're into ions. First one. Thing plus another thing equals that. I don't see any dissociation. I don't see any ions. Definitely not right. CH3OH, which is methanol, goes into water, creates methanol that's in water, that's dissolved in water. This is a non-electrolyte. There's no charges, right? There's no dissociation, no charges. Next one, Na2SO4, put it in water, 2 Na plus SO4, 2 minus. A, we have dissociation of the sodium and the sulfate, and we have a positive charge in the sodium, -2 charge in the sulfate. So this is going to be our strong, put strong E. So this is our answer. And the next one, this is methanol, same thing, put it into water. You get aqueous methanol, otherwise known as aqueous methanol, aqueous ethanol, which is ethanol dissolved in water. This is again, just like methanol, going to be a can I not spell electrolyte? There we go. Wow, that's really bad handwriting. Okay. So there we go. Good job. We got it right. Awesome. All right. So let's just talk about solubility. All right. So if you don't know about solubility, you end up like this guy or girl. Either way, pretty bad. So this is gout. So gout happens when the concentration of uric acid in the blood exceeds the solubility. Now, if you exceed a solubility, we're going to learn that it actually creates solids in your bloodstream. And create solids can create clots. It could clog up your arteries. It can mess up your joints, like in gout. So a lot of things can happen. Now, what is solubility? People don't really know what the definition is or how to teach it. So what I call it is the solubility is a threshold of dissolving. Threshold of dissolving. What that means is, if you have, let's just look at this example. Its solubility of 7 milligrams per 100 milliliters of plasma. This is the definition. This is the threshold. 7 mg per 100 milliliters of plasma. That right there. That is telling you that for uric acid, its solubility limit is 7 milligrams. Only 7 milligrams can be dissolved in 100 milliliters of plasma at 37 degrees Celsius. Also, temperature and pressure change the solubility. So that's why, to be very precise with what you say, you have to say two things. This is half right. I need to say at 1 ATM. But we assume that medical environment, whatever, it's always going to be 1 ATM because we're on Earth and we're not in Colorado on a mountain somewhere or in deep space. So it's going to be 1 ATM. Okay. So I'm going to say it one more time. The solubility is a threshold. If you have less than 7 milligrams in 100 milliliters of plasma, or that ratio, you're good. You can add more. But as soon as you add, let's say you have 100 milliliters of plasma, you add 6, you're good. You add 7, you're good. If you add 1 more milligram, that milligram will not dissolve. Only 7 will. If you add 1 more to make it 8, won't dissolve. It has reached and exceeded the threshold of solubility, the threshold of dissolving. And this threshold is a trait of each substance. So if you're wondering, oh, how did we get the solubility? It can easily be defined and measured, and you can figure it out yourself. What you can do is take a known amount of water, take table salt, and measure out an amount in grams of table salt. Let's say take and you can do it like teaspoons or whatever and convert to milliliters. Take 100 milliliters of water. Then you can take start out with like 10 grams of salt. Put it in. It'll dissolve. Take 10 more. Put it in. It'll probably dissolve. Take 3 more. Put it in. 5 more. 10 more. Take amounts, right? Eventually, you'll see that it starts to not dissolve. Once you have an amount on the bottom that doesn't dissolve, you can scoop that amount out, dry it off, and weigh it. So let's say you did this. This is a good home experiment you can try. I'll add a new slide. So, first step is 100 milliliters H2O. Then put in 10 grams of salt. If nothing happens and just dissolves, 10 grams of salt. Then put 10 grams of salt. Keep repeating this. Repeat until solid doesn't dissolve. Then scoop remainder. So scoop the solid that's on the bottom of the cup. Scoop it remainder, dry it, and weigh it. Take the weight. Yeah. So what that means, let's say you did 10 grams of salt, dissolves completely. Another 10 grams, dissolves completely. Out of this 10 grams, only 7 dissolved. That means you have 3 left, right? What you're going to do is you weigh that 3 out, you get 3. That means you have 7 in there. So that means the total amount dissolved is 10 plus 10 plus 7. 27. Therefore, you have a solubility. 27 grams per 100 milliliters would be the threshold. So you figured out experimentally the threshold, or the solubility of a substance in another substance at a temperature, at a pressure. And let's say all your homes, hopefully it is room temperature, 25 degrees Celsius, and it's not pressurized. You're in a pressurized chamber of any kind. Hopefully nobody lives in a submarine. So 27 grams in 100 milliliters. Then the correct way of saying that, you get it in grams per milliliter. So that would be approximately 0.27, or not approximately, that is 0.27 grams per milliliter. So that would be the solubility. Usually it's in grams per milliliter. That's the way we write it. So usually grams per milliliter. And in medicine, we use that a lot when we're giving dosages, or sometimes we give it milliliters per kilogram of body weight. That's a solubility also. But usually if we're talking about blood, it's milliliters or even deciliters. But anyway, I hope you understand that. If not, please ask me questions. Okay, so this is basically what I said. It is the maximum amount or the threshold amount that a solute can dissolve into a specific solvent. So you have to say that this is 100. This is the correct answer for this would be the solubility of salt in water would be 0.27 grams of salt per 1 milliliter of water at 25 degrees Celsius, 1 atm. That's perfect. Nobody can mistake in what you say. Some textbooks just write, oh, the solubility is 1 gram per mil. That doesn't mean anything. If we're talking about water, sometimes they assume water. Not all the time you can do that. Luckily, we're talking about mostly healthcare and things like that, so we can assume it's water, right? Nobody's blood has hexane in it. At least it shouldn't. All right, moving on. So that being said, there are 3 types of solutions, right? Strong electrolytes, weak electrolytes. No, not that again. We have saturation. Now, this solution, I already explained these different types, but we're going to go over it again. But I didn't use the terms. You can have a solution that's unsaturated, meaning it contains less than the maximum amount of solute. And it can dissolve more solute if you put some in. For example, if you have, let's say, this is just for the purpose, this is for example, salt in H2O equals 3 grams per 100 milliliter. Let's just say that's the solubility. If you put in 2 grams into 100 milliliter, you're having unsaturated because it didn't reach the limit and you could add more. That's it. Moving on. Saturated contains the maximum amount of solute that can be dissolved. It might have undissolved solute at the bottom. Okay, so saturated means you have completely reached the threshold, and you might have more. So there's different ways that textbooks. I don't even know what I agree with anymore. But saturated. This is the definition that we're going to use. I'll tell you the other definition in a second. So saturated is, let's say you have 3 grams of salt and 100 milliliters of water. As a previous example, that was our limit. If you have exactly 3, you're not going to have any that's dissolved at the bottom, and you're going to perfectly reach the limit of solubility. Or if you have 4 4 grams in 100 milliliters. Out of this 4 grams, only the limit will dissolve. So only 3 out of this 4 will dissolve. The remaining 1 will remain at the bottom, will be at the bottom of the container. So that's how solubility works. Whatever the limit is, the solution will dissolve the solute up to that solubility limit, and everything that comes after that will just be undissolved solute or solid solute at the bottom of the container. The other definition they say for saturated is it's exactly the maximum and no more. That's very rare. But then you have supersaturated, which is more than the limit. But we're just going to call it saturated for now. Anything that's at the limit or more, saturated. Okay. Next, this is saturated. That's basically what I explained. Next, identify each of the following solutions as saturated and unsaturated. Salt disappears when it's put in water. Now, by a glance, you're like, oh, that's unsaturated, right? I don't know, right? Did we reach the limit? If we reached, I was about to say roached. If we reached the limit, exactly the limit, we have no way of knowing unless we put more in. So if the salt disappears when it's put in water, that means what they're going for is it's unsaturated. But we actually don't know because it could have reached exactly the limit of solubility. In that case, adding more would tell us the answer. B, sugar added to a cup of water does not disappear but sits at the bottom. That means the solution is definitely saturated. It's reached the limit and has gone over the limit. And everything you add additional will not be dissolved. So yeah, for A, they were going for unsaturated, but technically you don't know. But I think they were meaning before you did this, what was the solution? So if you beforehand you have a solution, then if you put in salt and it disappears, that previous solution was unsaturated. So that's probably what they meant. All right, moving on. So at 40 degrees, the solubility, see how they specify? The solubility of KBr is 80 grams into 100 grams of water. Identify the following solutions as either saturated or unsaturated and explain. All right, so solubility limit, the threshold, 80 to 100. All right, 60 to 100. That's good. Under the limit. That just reminded me of the drunk driving commercial. Under the limit. No, it was over the limit, under arrest. I think that's what it was. Yeah, so don't drink and drive. Well, don't go outside at all, but whatever. So you have 60 grams. It's under 80 grams in 100 grams of water. You're good. It's unsaturated. Next, 200 grams of KBr to 200 grams of water. Now we're not dealing with 100 grams, but 200 grams. So to figure that out, we can just double this. So if you double this, it's 160 grams to 200 grams. That's the limit. We're over the limit. 200 grams, 200 grams. Over the limit, under arrest. Not the answer, or not. All right, sorry, I don't know why I crossed that out. We're not really looking for which one's unsaturated. This is saturated. I'll just put sat. And this one's unsat. Next, 25 grams of KBr, 50 grams of water. This time, we're not multiplying the amount. We're dividing the amount, or the threshold. So we divide the threshold. We get 40 grams per 50 grams of H2O. Therefore, yeah, looks like we're under the limit, right? 25 grams of KBr into 50 grams of water. The limit that we can get to is 40 for it to dissolve. So we're good. That's unsaturated. Cool. All right, good. Oh, wait. There we go. Good. Okay. So, like I said, different things have an effect on solubility, whether it be the temperature or the pressure. And I think we don't touch on pressure. Oh, we do. We do. Okay. But basically, to cut to the chase, I'm not going to test you on this specific thing, but just know that it has an effect. Know that temperature and pressure have an effect on solubility. And think about how it happens molecularly. We learned about temperature. We learned about the effects, especially when we talked about gases. We learned about speed of the molecules. So, if you increase the temperature, looking at this graph, increase the temperature this way, you are speeding up the molecules. right? Most solids increase. That's stupid. Okay, but whatever. Let's look at that. This is solids. Solids into liquids. That's the only thing that's important. This doesn't really explain it too well. But for solids, the more speed you have, right? The more temperature you have, the more speed you have of the molecules. The more speed you have, the more molecular collisions you have with the solvent. The more collisions that let's say, NaCl particle has with a solvent, the more likelihood of that solvent dissolving the solute. So basically, the increase in temperature leads to an increase in solubility, because the speed and the more frequent collisions of the molecules to the solvent, the solute and solvent, allow the solute to take in the solvent more easily. So that explains all these curves. NaCl is actually not too, doesn't really change that much with response to temperature, but I'm pretty sure if you go above 100, it starts to do this and go like exponential. But at normal temperatures below the boiling point of water, it's pretty stable, unlike glucose, right? Okay, this is for solids going into liquids. For gases, it's the opposite. So as the temperature increases, and it kind of makes sense, and I'll explain to you why. I'm not going to write anything, but solids, right? Solids going into liquids, dissolving. When you're dissolving, the way dissolving occurs is that the solvent actually rips apart the solute based on charges. So here's what okay, now I have to write. I'll make a new slide. This is actually really interesting, and getting into the molecular mechanism of dissolving. Here's a water molecule, right? Is the oxygen. Oxygen is negative charge, and hydrogen is positively charged. NaCl, solid. When a water molecule goes up to NaCl, it doesn't just say hi and run away. That's what gases do. They don't react with each other. For solids and liquids and in solutions, they can react with each other, and that is how they dissolve. So, the hydrogens, and keep in mind, there's hundreds of waters, a lot of them, all around the NaCl. All of the positively charged hydrogens from the water will attack, and that's the organic chemistry term, is attack. They will attack the chlorine. Other water molecules over here, their negatively charged oxygen will attack the sodium. I don't know why that happened. Will attack the sodium. The sodium and the chlorine would be bombarded by different water molecules, eventually splitting them up. The water will get into the crevices between Na and Cl and actually break them apart, and their relationship is over. Na plus Cl minus will be separated, and they will be engulfed by water molecules. Like this. Sodium will be like that because the hydrogen... Oh, no, actually, no. Sodium... Nope, that's wrong. Sodium will have all oxygens around it, and chlorine will have all hydrogens around it because of the charges. Let me do that again. So sodium is positive. It'll have negative oxygens all around it, like that. Here's the water. Like that. It'll be like that. The chlorines will have positively charged hydrogens all around. You get the point. They're going to be all around. So solid into liquid. Solid into liquid depends on charge interactions. That's the key. So it depends on interactions that involve charges. Wow, it's really sloppy. But hopefully you understand. For gases, that's the opposite. Gases, remember, we talked about, they do not have a very large, or they have basically no attractive force to one another. So if you, going back to this graph, if you speed up, so you increase temperature, you increase the speed. If you increase the speed of gas particles, they're going to go faster, but they're actually going to that will speed up their interactions, but there's no charges involved in those interactions. There is no attractive or repulsive forces that dictate or that control a dissolving behavior. So for them to go together will be tougher, actually, because there'll be more collisions. So it's kind of like, I don't know. That was a bad attempt. I don't know. I don't know what the hell I'm talking about. But all the scientific things I said are correct. I just can't think of a good example right now. But gases, as you speed up the molecules, they're going to increase their collisions, which is a bad thing in terms of solubility. That means there's going to be just more excitement of their molecules, which leads to them just bouncing off each other, not really dissolving fully together. And that's the opposite of when solids go into liquids, because solids have a charge-mediated dissolution. I like that term. I just made that up. I'm sure it's a thing, but I like that. If you say that, people will be like, holy crap, they're a scientist. Charge-mediated dissolution. So they have a charge-mediated dissolution. That's why solids' solubility increases as the temperature increases. Okay? So there we go. For gases, we talked about why that is. All right, so why could a bottle of carbonated drink possibly burst when it's left out in the hot sun? All right, so you can think about that. You can pause and think about it, but I'll tell you the answer right now. So when it goes in the hot sun, temperature is going to increase. A carbonated drink is carbon dioxide put into a liquid. So when it gets hot, the carbon dioxide particles that are in the liquid are going to want to get out. Their pressure increases, and because they're moving faster, and they're going to have less time to really interact because there's no charges mediating the collisions. They're just going to bounce off of every water molecule, and they're going to get really excited. If that's the case, they're going to bubble, and they're going to explode and burst. Okay, why do fish die in the water that is too warm? In water that's too warm. So you can think about that again, but I'll tell you the answer. So they need oxygen to live. If the water is too warm, the solubility of oxygen decreases in the water for the same reasons mentioned before. Therefore, they will have less oxygen to live, and they will die. So that sucks. Okay. Next. Oh, that's the answers. Cool. All right, so solubility and pressure. Are we learning Henry's law? Oh, we're just going to talk about it. We're not going to learn the... Yeah, okay. Henry's law is how solubility relates to pressure. And there's an equation for it. Basically, if you understand what I said before about the Coke, or not, this is the Coke, about the water, about the carbonated drink in the hot sun, it kind of very, very similar concept. So, here's how it works. Let me see. I don't remember seeing this. All right. So if you have a Coke can, right, and it's closed, it's under pressure. CO2 is in the can. That's what makes carbonated drinks. It's just CO2. The reason why there is no fizzing before you open the can, it's just a very flat liquid. There's no bubbles. The reason why is because the CO2 in the top and what we call the headspace is under such a high pressure that, and you can think of pressure as a force. Remember, it's force per unit area, right? So we're pushing down the pressure of the headspace between the liquid surface and the top of the can. It creates a high pressure where it's pushing down on the liquid. If it's pushing down on the liquid, it's physically keeping the CO2 molecules in the liquid dissolved. So a high pressure creates high solubility, better solubility in gases into liquid. Because the pressure, I wish you could see my mannerisms, but I'm like kind of like forcing, like pushing down, right? So it's kind of, the pressure is pushing the CO2 molecules down into the solution physically, so they can't get out. Therefore, they are forced to have a higher solubility. That's all that Henry's law is. So I may ask a conceptual question about it, but that's it. Okay, so there are a bunch of soluble versus insoluble compounds. Here's the solubility rules for ionic compounds in water. And we're not going to go over them. You're not going to have to memorize them, but I will tell you if you need to know them on the question. So here's an example of things that are insoluble. Here's what you would see. So if you mix different solutions together that are soluble, sometimes a double replacement reaction might occur in which the products are insoluble. So let's do an example of that. You don't have to do this for the lab. So I'll get rid of this. Wait. There you go. Get rid of this. All right. So let's try to react something. Let's get cadmium nitrate plus Na2S plus sodium sulfide. All right, if you react these, this is a double replacement reaction. You have two ionic compounds, and both of these are soluble in water by themselves. If you mix them together, they will go through a double displacement reaction. The double displacement means double replacement. Sorry, I said displacement. Double replacement. So what that means is both of the anions replace each other, or cations, however you want to think about it. So CD would go with S, and Na would go with NO3. And to balance it, it would be 2 right there. This would be aqueous, and this one would not be aqueous. This would be solid. This would be aqueous, and this would be aqueous. Okay. The reason why is because cadmium sulfide, according to this picture, is not soluble. It creates this cool-looking orange, what we call precipitate, or solid. So, if you react two aqueous compounds together, that when they switch around and reform, you get an insoluble compound. That insoluble compound will be visible because it'll form what we call a precipitate. And that precipitate is a solid, could be crystal, it could be a cool color like this, like these, but most of them are just like milky. They're like foggy white milky, like crystals. So it's not really as cool as these, but these are just the really cool ones they picked. So hopefully you understand that. Okay, we don't have too much longer. So we're on slide 45 of 67. All right, so we kind of covered that. All right, concentration, the last big concept. Now, concentration, I'm sure some of you who are working in a hospital or work in a doctor's office are comfortable with some of the calculations involving concentration. But basically, we can prepare concentration in different ways, in different units for it. So what the concentration is, and I always use my orange juice example. So I am lame, and I like to dilute my orange juice. It's too sweet, and also I don't know, poor college student life. I just kept that trait that I just dilute my orange juice with water. Whatever, I get more orange juice out of it. But do you actually get more orange juice? No, you get more liquid, because you are taking these solute particles and you are dissolving them along a larger amount of solution. You're not getting more orange juice particles or citric acid from that. You are just basically spreading them out. So it seems like it's more. That's what concentration is. It is the amount of solute, or the amount of orange juice particles, per amount of solution. And there's different ways of measuring it. It can be expressed we'll talk about that right now. So here's some of the ways. We're going to talk about molarity as the main way, but here's some that are common in healthcare. You have mass percent, which means that, let's say you put in 10 grams of salt into 100 grams of water. It'll be 10 grams of salt into 100 grams of water. It'll be 10 grams over 110 grams of solution. Solution, solute. So the percentage there would be, what is that, like 9%? It'll be like 9%. So that's the mass percentage. Then you have mass percentage. Oh, that's it. Yeah, okay, so mass percentage. Yeah, that's one of them. Then you can do, so keep this in mind, you could do a lot of different ones. You could do mass to volume, volume to mass. There's different ways of doing it, but mass percent is the most important one. Then there's molarity. Molarity is, in chemistry, the most important one, not necessarily in healthcare. But in chemistry, we like moles of solute per liters of solution. Okay. So this one is just a standard. It's the SI unit for concentration, molarity. And it is a strict definition of the moles divided by the liters. And that equals molarity. Molarity is measured big M. So a 1 molar solution of NaCl is defined as every 1 liter of it has exactly 1 mole of NaCl. Follow-up question. How many grams of NaCl is that? Oh, I know how to do that. I can do stoichiometry. Or not stoichiometry. I can do mole calculations. Also in Crash Chem. Hashtag Crash Chem BMCC. Get on that. So 1 mole of NaCl is 58.2, I think. I don't know, 58.2 grams. So this is, you could say that, oh, we have 1 mole per liter, 58.2 grams per liter. Same thing. But this is the molarity. 1 is 1. So let's do examples. What is the molarity of 0.5 liters of NaOH that contains 6 grams of NaOH? All right, we're going to get rid of all this. Oh, the answer's right there, damn it. Whatever, we're going to do it together. Step. All right, so what is the molarity of 0.5 liters? So the molarity equation also will be given on the exam. Big M equals moles per liter. 0.5 liters. That's given. Nice. So L equals 0.500 liters of NaOH solution if it contains 6 grams of NaOH. We don't have the molarity. We're looking for that. And we don't have the moles. But we can find the moles using the molar mass of NaOH. So if you need, again, it's been a while, so if you need to refresh, definitely go on Crash Chem. There's mole calculations. You can refresh and get all the information. So NaOH, the molar mass of Na, 23. Molar mass of oxygen, 16. Hydrogen is 1. Add all those up. 33, 39, 40. 40 grams per mole. That's the molar mass of NaOH. Now, to figure out the moles of NaOH, that is in 6 grams. You do 6 grams, see how many times 6.00 goes into 40, and let's get my calculator out. 6 divided by 40, 0.15. 0.15 moles. Alright, so now that we have the moles and we have the liters, we can determine the molarity. 0.500. Oh, no. Do it down here. 0.15 divided by 0.5. So you get 0.3 m. This is the correct way to write it. So you write whatever the answer is, big M. That's the notation. Okay. Moving on. Let's do another example. So if you have 37 milliliters of Na2SO4, 37 milliliters that has 23 grams of it, right? What's the molarity? So, same thing. We need our big M equals moles divided by liters. If that's the case, then we have our liters, our volume, in milliliters. We need to convert it. So the bottom, 0.037 liters. That's how you convert from milliliters to liters. You can go from here, 1, 2, 3. Like that, and you put a 0. That's what it would be. Okay, next, moles. We have Na2SO4. And again, I know I'm going fast, but you can slow it down, repeat it, so please do that. I'm just really hungry. You're not you when you're hungry. Yeah, I'm not. I'm like hangry. So Okay, Na2SO4. Na2SO4, molar mass. 4 times 16 for oxygen. What was that, 48? That's not how that works. I think it's 60. Wait. I'm stupid. Hold on. I can do this. 64. There we go. 64. This is going to be on YouTube, and I'm going to disable comments because people are going to blast me for this. 64. Yo, you a professor? Who you think you is? That's what they're going to say. Not you guys, of course. Anyway, so grams per mole. Nope, that's not true either. Oh my god. So 64 grams of oxygen, 32 grams is sulfur, approximately, and 23 times 2, or 46, I could do that one, is just a sodium. Adding those together, you have 46 plus 32 plus 64 is 142, and that sounds right to me. 142 grams per mole, and that is Na2SO4. So now we have 23 grams of Na2SO4, dividing it by its molar mass to figure out how many moles we have, so we can figure out our molarity, and that is 0.162 moles. So that's good. Then we can do our molarity, so we could do 0.162 moles divided by our liters, which is 0.037. Divided by 0.037. And I get, do it on your own, 4.38. Big M. That's what I get from molarity. That's pretty concentrated. Okay. Good. Good. Also keep in mind, on the test, there might be ones where I give you the molarity, but I don't give you the moles, and I give you the liters, or I give you the liters and I don't give you the moles. There might be some combination of two. You get 2 out of 3. Okay. Dilutions is the last formula. So dilutions, like I said, you dilute the orange juice. And you can calculate the amount that you need or the concentration that you get from dilutions when you know the other traits. So we know what a dilution is. I talked about it. Basically, you're adding a solvent, not necessarily water, but you're adding a solvent, and it increases the volume, decreases the concentration, but the mass of the solute remains the same. That's key. Because if you take these particles, let's say this is orange juice, right? You take water, you put it in. You're taking the orange juice molecules and dispersing them over a larger area. You're not necessarily making more orange juice particles. So the volume increases, concentration decreases, amount of solute remains the same. That is those are the key concepts in a dilution. And there's a formula. The formula is the concentration 1 times the volume 1 equals the concentration 2 times the volume 2. Very similar to P1V1, right? This is C1V1. They work exactly the same way. There's an inverse proportionality between concentration and volume when you're diluting. So if you look back, volume increased, concentration decreased. Oh, look, they're inversely proportional. One goes up, other one goes down. So that's exactly what we're doing here. So you can use, and it also, when we talk about 1 versus 2, that means initially before it's diluted, and then finally after it's diluted. Okay, moving on to an example. Okay, so we have, what is the final concentration when 0.5 liters of 6.0 molar HCl is diluted to a final volume of 1 liter? Okay, you can pause it, try on your own, but I'll just keep going. Keep blasting through it. We want to use the same approach that we did for the gas laws, which was write everything we have down first and then put it into the equation. So we know our equation, C1V1 equals C2V2. I don't know why that came on the screen. Versus C2V2. Then we know our C1, right? So what is the final? It keeps coming up. I think I keep clicking the button on accident. Okay. So C1, what is the final concentration when V1 of this, when the volume of this is diluted? So it's always good to, context clues, very important to read the sentence. maybe multiple times if you need. What is the final concentration? Off the bat, what is the final concentration? Doesn't tell you C2. Tells you automatically that we're looking for it. All right, this is going to get really fucking annoying. Oh, I just said the F word. I'm sorry. Don't tell on me. Oh, now you have proof that I said the F word. Oh, no. All right, this is getting really... Good thing we're almost done. Okay. So C1, so the final concentration, we don't know. When 0.5 liters, that's the V1. He's testing my patience. 0.5... Okay, I'm going to write with the mouse. 0.5 liters, 6.0 molar. V2 is what we were diluting it to. So we're diluting it to a final volume of 1 liter. Okay. So then we're just going to plug it in. We're going to plug in 6. Volume 1 is going to be 0.5. C2 is unknown. V2 is 1. So we're just going to be V2. So then you just solve for that and you get 3 equals C2. Okay. We're good. Good. All right. So that's really not going to get much more difficult than that. Yeah. So you solve it and you get 3. So your concentration would be 3 molar. So once you dilute, and if you think about it conceptually, you're taking 0.5 liters and you're diluting it to 1 liter. So double its original volume. If you're doing double the original volume and it's the same amount of solute, the solute is going to be half times as concentrated, half as concentrated. And it makes perfect sense that the answer is 3 molar when we started out with a 6 molar solution. So hopefully that makes sense. All right. What is the molarity of a solution prepared by diluting this? So, okay, we can go through it. They have the answers. So you can try this on your own. I'm not going to type it. I'm not going to write it out because whatever's happening with my pen thing is annoying. What is the molarity of a solution prepared? So what is the molarity? It's already telling you M2 is unknown. Or sorry. Sometimes you call it M2, but C2 is unknown. Concentration 2 is unknown. Of a solution prepared by diluting this. This is V1. This is V1. Diluting this of this. 0.6 molar to 0.54 liters. So you're diluting V1 of C1 to V2. What is C1? What is C2? So we could do the same exact approach. Sorry if that sounded complicated, but very similar. Just plug it in and then chug it. You solve for the second M2 concentration after the dilution, and you get 0.2 molar. Okay, the last thing we're going to cover is in this slide, and that's it. So, in healthcare, a lot of times you have different problems with cells based on fluid that's in the blood and different concentrations in the blood plasma concentrations. And this is why we use isotonic saline. So sometimes when the concentration inside the cells and the blood gets thrown off, you can have problems. And these problems, there's different types of solutions. Not meaning answers, but liquid solutions. So normally we like to think our cells and our blood, let's say our blood cells and what we call interstitial fluid or water molecules in between the cells. We like to think the concentrations of ions between those two regions, inside the cell and outside of the cell, are equal. If they're equal, we have an isotonic solution. Now, that's good. Remember, I think on my Tuesday class I stressed this more than my Friday class, but everything works in a gradient. That's how everything moves, naturally, without any external energy. Gases, you want to go from a high pressure to a low pressure. A waterfall goes from a high point to a low point, a high potential energy to a low potential energy. That is how the universe works, and that's how things move. It's by going from a high state of energy or pressure or concentration and going to a low state naturally to balance out and make an equilibrium. In isotonic solutions, that equilibrium is reached. In hypotonic solutions and hypertonic, an attempt by the solution to reach those equilibrium conditions is attempted, but it's not necessarily met. Sometimes it is, but sometimes it's not. So, a hypotonic solution means that the concentration of, let's say, ions inside the red blood cell is a lot lower than outside the red blood cell. What that means, it means the solution is going to try to equilibrate, the concentrations by osmosis. And what that means, osmosis means the movement of water. So the movement of the fluid is going to go into the cell to try to dilute the internal ions of the cell, to try to get to the concentration that they're at outside of the cell. Sometimes that works. But if you have too much fluid into the cell and it still doesn't reach equilibrium, the fluid doesn't know any better. It doesn't know that, oh my God, you're going to kill the cells, please stop. No, it keeps going until the cell bursts. And sometimes you get what we call hemolysis, caused by, meaning, or that's just for blood cells. You get a lysis. Lysis means splitting. Hemolysis just means refers to hemoglobin, blood. You get blood cells can burst. So when you have a low concentration outside of the cell, lower than the inside of the cell, the fluid will try to go into the cell to try to equilibrate those concentrations, and you'll get the cell will explode. Then you have the opposite, hypertonic solutions. Hypertonic, you have a high concentration of solute outside of the cell, a low concentration inside. So then the water from inside the cell tries to leave the cell because it wants to equilibrate, it wants to raise its own concentration by, it's basically undiluting, it's concentrating its own ions by making water leave the cell, and it what we call crenates the cell, or makes it very small. It decreases the volume and increases the concentration in order to equal the interstitial fluid, the outside water fluid. So hopefully those make sense. Here are the slides for them, just so you can see it. You can pause it here. I basically explained this already, but yeah, that's hypertonic. And then the last thing is dialysis. Uses the same technique. So a dialysis technician is somebody who does this with dialysis for the kidneys. Basically what happens is you can hook up a person to a dialysis instrument. I'm not sure, I've never seen one before, but in this picture there is one. But the mechanism of how it works is, if you have, so your kidneys filter a lot of urea and a lot of waste, right? So urea is not a good thing to have in your kidneys, right? In your liver, in your kidneys, or in your body. So we want to have a low concentration of urea. If your urea concentration in your blood gets too high, you can get gout, just like we saw on the first slide. So everything connects. Now, if the concentration is too high, what they can do is they can dialyze your blood. So they can take out your blood, and they can do this at, I don't know how often it's done, maybe some of you do, but they can dialyze your blood and pump your, what we call urea-saturated blood through a membrane or a container that has dialysis fluid. This dialysis fluid, the urea, will actually diffuse through this membrane and try to equilibrate the concentration with the container. And the container has a very low concentration of urea. If that's the case, then when the urea leaves, it's going to try to equilibrate a very high concentration of urea in the blood to a low concentration, meaning a lot of the urea is going to come out. Until eventually, if you keep pumping blood and urea is kept being put in here, they will reach an equilibrium. But there'll be a lot less urea in the blood. Then, when an equilibrium is reached between the urea in the blood and the container, we can just simply switch out the containers with new liquid. If you switch out the containers, more urea comes in with the blood, and you dialyze it out again. So you're basically removing, you're using the pressure, the concentration gradient from high concentration of urea in the tubing to low concentration in the diacylate to remove urea. You're using that concentration gradient to remove urea and other waste products from the blood. And you could do multiple rounds of this dialysis by keep switching out the container. And you can do this for an hour. I'm not sure how long it takes either. I've never seen it done, or I've never done it. But I've done dialysis with proteins and stuff where we change out the buffer. We try to, we want a protein in a different buffer or a different solution. We do this technique, but we don't use like blood tubing like this. We use it like a little baggie. Anyway, so that's it. That's it. So thank you for listening. Here's different videos on molarity, dilutions, and understanding solutions with everything we learned. So I hope you guys have a safe weekend, and hashtag CrashChem. Definitely take a look at that. Yeah, so I'll be posting more videos probably next week or even during the weekend. Okay, so good luck, everybody. If you have any questions, let me know. Feel free to schedule a call with me. Don't just cold call me. I probably won't answer because I'm usually really busy. But definitely schedule a phone call with me. A lot of you did that already, and apparently it was very helpful. So thank you, and good job. Have a good night. Awesome.